Welcome to Unit 2, problem set questions 9 through 11 answers. In these questions, we're going to focus on resonance structures, and resonance structures are the movement of electrons. So in these questions, what we're going to do is we're going to, using curved arrows, show the movement of electrons, draw a sequential resonance structure of the following ions. So here's our first structure. Here we've got an anion. And before we begin, what we need to do is to see if there are going to be resonance structures. And the way that you do that is you look next door, the atom next door to your charge, and is this atom here part of a multiple bond or has a lone pair? The lone pair would be specific for cations. In this case, we have an anion. So is the atom here part of a multiple bond? The answer is it is. Therefore, we do have resonance structures. Now, the one thing to keep in mind when dealing with anions, okay, anions are the or have the highest electron density. They are electron rich. They are going to push multiple bonds out of the way, i.e., they are going to push the electrons in the multiple bonds, specifically the electrons in this double bond, out of the way and onto this oxygen. When we're dealing with anions, there's always two arrows, okay? And so what's going to happen is these electrons here are going to roll down and form a new carbon-carbon double bond. Now, when this occurs, we can't just leave it that way. We can't just make the double bond and go on our way, because what happens now is this carbon will have 1, 2, 3, 4, 5 bonds to it, and you can't have pentavalent carbon. And so what happens is that the electrons in the multiple bond between carbon and oxygen get pushed onto the oxygen. And what you create is this. See that now the excess electrons that were in this multiple bond are now on the oxygen, and we now have a negative charge on our oxygen because we're going to have 1, 2, 3, 4, 5, 6. And if you count that electron there, that would be 7. Oxygen should have 6. It has 7 electrons, therefore it has a -1 charge. And you can see there's no charge here. And our charge then has gone from here to there. So it goes every other atom in this case. Okay? But you see, in the case of an anion, it did the pushing. It pushed the other electrons out of the way. It pushed these electrons in this multiple bond onto the oxygen because it is the highest electron density, and therefore it is pushing other things out of the way. Now that we have this structure here, are there any other resonance structures? Well, there are no additional resonance structures that wouldn't repeat. That's why I say sequential resonance structures. We could go back and make the double bond here and kick these electrons back onto the carbon, but that doesn't get us anywhere. That doesn't give us new sequential resonance structures. So in this case, these are the only two resonance structures. Now let's deal with a cation. And a cation, specifically right here, it's a carbocation. We're dealing with a deficiency of electrons. There are not enough electrons around this carbon. It is often described as a hole, especially in inorganic chemistry and in polymer chemistry, because electrons flow to the hole. They flow to the carbocation. Okay, so think about it this way. If you pull the stopper in a bathtub full of water, the water rushes towards the hole. It's the same thing here. The electrons are going to flow towards our cation. So that means our electrons, right, from a neighboring multiple bond or lone pair are going to start from there and move towards that carbocation. Okay, so in this case, we've got our carbocation. We look next door. Okay, over here, is this carbon part of a multiple bond or have lone pairs? No. Okay, so we can't have a resonance structure going this direction. We look over here. Sure enough, it is. This carbon is part of a multiple bond, and therefore we can have an additional resonance structure. So again, carbocations are holes. They are deficient electrons. We draw resonance structure starting from high electron density going to low electron density. So we're going to start from the middle of this double bond, and the electrons are going to go right there to form a new double bond between this carbon and that carbon. And that will give us the following resonance structure. Double bond is there. Now this was where the double bond used to be. So let's look around. Let's use formal charge to our our benefit here. This carbon is going to have 1, 2, 3, 4 electrons around it, right? So it should have 4, so this is going to be neutral. This carbon here, if you count the electrons, half the electrons in the bonds, has 1, 2, 3. Well, it should have 4, so 4 minus 3 is positive 1. Our positive charge now is right here on that carbon. Are we done? Well, the way that we see if we're done is we don't want to repeat, so we're not going to go back this way. We're going to look out this direction. So we look to the atom next door. Okay, this is a carbon. Is this carbon part of a multiple bond, or does it have a lone pair? The answer is it's part of a multiple bond, so we're going to have an additional resonance structure. Our electrons are going to flow from this double bond to form a new carbon-carbon double bond between these two. So we're going to draw that. Now our double bond is there. And so let's use formal charge. We've got to find out where that positive charge ended up. Well, this guy, this carbon here, 1, 2, 3, 4, it should have 4 valence electrons, therefore it is neutral. This one right here, you can tell something's not right. It only has 3 things attached to it. Carbon normally has 4. So if we count them, 1, 2, 3, well, carbon should have 4 valence electrons. In this case, it has 3, so 4 minus 3 means that it would have a positive charge. So our positive charge is going to be on that carbon there. Are we done yet? Well, what we got to do is we look past our carbon here going in this direction. If we go this way, if we look this direction, we'll just be going back and repeating structures. So let's look at this. We've got a nitrogen. Is our nitrogen part of a multiple bond? The answer is no. Does it have a lone pair or unshared electrons? The answer is yes, it does. And it can use these unshared electrons to form a new double bond, just like this. They're going to roll in there and make a new carbon-nitrogen double bond. So let's draw this out. We'll draw a ring first. Carbon, H. Now we have a double bond here in our nitrogen. So let's take a look at what we got. So if we look at this carbon, it's got 1, 2, 3, 4 electrons around it, counting half in each bond. So carbon should have 4 valence electrons. This one has 4 valence electrons, therefore it's neutral. Now let's look at nitrogen. Nitrogen should have 5 valence electrons. Let's see how many we got here. 1, 2, 3, 4. So that'd be 5 minus 4. This would be plus 1, and our positive charge now would be on our nitrogen. Now we see, are we done? Well, I don't know. We have to look further. we can't go, if we go back this way, we're just repeating, and we're never going to make resonance structures to hydrogen. So yes, we are done. So in this case, we have 1, 2, 3, 4 resonance structures, and we drew 1, 2, 3, 3 new sequential resonance structures. Okay, we're going to continue practice resonance structures. We're going to do the exact same thing as we did on the previous slide. We're going to, using curved arrows, we're going to show the movement of electrons, drawing sequential resonance structures of the following ions. So we look here, we see, okay, we've got our charge here is a negative charge, which means our anion is going to be pushing things out of the way. It means our arrow is always going to be starting from our negative charge because it is the highest electron density. And so before we start, we know we have a charge. Now we have to look next door to the atoms next door to see if they are part of a multiple bond. Well, this carbon is not part of a multiple bond, so we can't go in that direction. There's no resonance structures this way. If we look over here, this carbon is part of a multiple bond, and therefore we can have additional resonance structures. And so our anion is going to roll in and form our carbon-carbon double bond. But remember, anions push. They're going to push electrons out of the way. So the electrons in this double bond are going to go on to the carbon atom, just like that. And so let's draw this out. CH3, carbon, H. Got our lone pairs are there. Now, let's make sure that we've got the charge in the right place. Now, it's easier with anions because you can see the lone pair, but the lone pair is here. So this would be where our anion is, but let's prove it to ourselves. And so if we look where we started, look at these carbons. So this carbon that was the anion has 1, 2, 3, 4 valence electrons. So carbon should have 4. This one does have 4. It's neutral. Carbon, again, should have 4. This carbon has 1, 2, 3, 4, so it's neutral. Let's take a look at this carbon here, the one that has the lone pair on it now, or the unshared electrons. Carbon should have 4 valence electrons. This one has 1, 2, 3, 4, 5. So 4 minus 5 is -1, and that is where our anion is. So now, are we done yet? Well, I don't know. What we have to do is we look next door. We don't look this way because we'd be going back and repeating structures. We don't want to repeat structures. So we look over here. So is this carbon atom here part of a multiple bond? Well, it is. So we have additional resonance structures. So our anion is going to swing down and form a new carbon-carbon multiple bond, double bond here. Okay. But when it does this, remember, it's got to kick these electrons out of the way, and they're going to go and onto the other atom of the multiple bond. In this case, it's going to go to the nitrogen, depositing another lone pair. So we'll have 2 on that nitrogen, just like that. And that will yield the following. Just like that. So let's count our electrons around this carbon first, because this is where the anion was. We got 1, 2, 3, 4. Carbon should have 4, so therefore this one's neutral. Now let's go to the nitrogen here. You can see we added extra electrons, i.e. another lone pair. That should tip you off that we are going to have the negative charge is going to be on that nitrogen. But if you look, we got 1, 2, 3, 4, 5, 6 around this nitrogen. Nitrogen should have 5 valence electrons. This one has 6. Therefore, 5 minus 6 is -1. This is going to have the negative charge on it. Are we done yet? Well, again, I don't know. Let's look. We can't really go any further. If we go this way, we're going to repeat. We can't have resonance structures onto hydrogens. So yes, this is the end of new sequential resonance structures that we can have. Our next example here In this case, we got a cation. So cation is a hole. Electrons are going to flow to the hole. Okay, they're going to flow just like water flowing down the drain. So here's our positive charge. We look next door to see if our atom has a lone pair or is part of a multiple bond. In this case, it is part of a multiple bond. So we will have an additional resonance structure. Our electrons are going to flow from the double bond in between these two carbons to form a new double bond. And that's going to give us the following structure. Oops. Now we got to find out where the positive charge is. It's easy to lose positive charges. This is why I'm being very methodical when we try to figure this out. In this case, if we look, put in our electrons around our atoms. This is where it started. Let's start over here. 1, 2, 3, 4. So this carbon owns 4. So at that point in time, carbon should have 4 valence electrons. This one does have 4, so 4 minus 4 is 0. There's no charge here. Again, this looks a little strange because it only has 3 things attached to it, and your eyes are going to start picking these up. So carbon should have 4 valence electrons. This one has 1, 2, 3, so it has not enough. So 4 minus 3 is positive 1. Our positive charge is right there. Are we done yet? Again, I don't know. We have to look. Over here, now this atom is not part of a multiple bond, and it also does not have a lone pair. This carbon is part of a multiple bond, so we can have an additional resonance structure. The electrons flow towards the hole, so they're gonna swing over here and form a new carbon-carbon double bond right there. So draw it out. Draw it in a different color this time. Carbon. Like this. So let's check, make sure we got to go find our positive charge. So that's where it used to be. So 1, 2, 3, 4. Carbon should have 4. 4 minus 4 is 0. This carbon here again, 1, 2, 3, 4 electrons. Carbon should have 4. This one has 4. It's 0. Now let's take a look at this guy right here. 1, 2, and 3. Carbon should have 4. This one has 3. So therefore, it's 4 minus 3 is positive 1. That's a positive charge. Are we done yet? Again, don't know. What we need to do is we need to look next door to see, is the atoms next door, do they have lone pairs or are they part of a multiple bond? Well, this oxygen is not part of a multiple bond, but it definitely has lone pairs, so we can use those to form another resonance structure, just like this. The electrons swing in to form a new bond between carbon and oxygen. So we're going to have a double bond there. That's going to give us the following. If we go to our carbon here, it's going to have 1, 2, 3, 4 electrons. It should have 4. It's going to be neutral. Our oxygen now, because we've got to go find our charge, our oxygen has 1. Let's draw them in here. 1, 2, 3. 1, 2, 3, 4, 5. Oxygen should have 6 valence electrons. This one has 5, so 6 minus 5 is positive 1. Our positive charge now is on our oxygen. Are we done yet? Well, if we look next door, this carbon is not part of a multiple bond or a lone pair, so therefore this would be the last structure and we're done. Question 11 is just more practice doing what we've been doing on the previous slides. So let's zoom in here. Here we've got an anion. We look next door to see if we have resonance structures. Is our atom next door part of a multiple bond or have a lone pair? The answer is it is part of a multiple bond. So therefore, we are going to have additional resonance structures. Anions do the pushing. So therefore, those electrons swing in to form a new carbon-oxygen double bond. These electrons have to go somewhere. They're going to go to the carbon atom. That's going to give us the following resonance structure. Lone pair is there. These will get much easier to draw once we learn what's called bond line form in the next unit, which is therefore you don't have to put in your carbon, the C's for carbon. So right here, let's take a look at this carbon atom. It's going to have 1, 2, 3, 4, 5 electrons around it. It should have 4. Therefore, this is where the anion is. Okay, our oxygen you can see is neutral now. It's going to have 1, 2, 3, 4, 5, 6. It should have 6, therefore it's neutral. We look next door. Is this atom part of a multiple bond or have a lone pair on it? The answer is it's part of a multiple bond, so we have additional resonance structures. So these electrons are going to swing in and form a new carbon-carbon double bond. That's going to require these electrons being kicked out and placed on that carbon atom. It's going to give you this. Like that. This is going to be our negative charge. If you count, 1, 2, 3, 4, 5. Carbon should have 4, so 4 minus 5 is negative 1. Almost forgot to put these hydrogens on. If you look where we started from, this carbon has 1, 2, 3, 4 electrons that it owns. It should have 4 electrons to own. Therefore, it is going to be neutral. We look here, are we done yet? I don't know. We look next door. This carbon is part of a multiple bond, so we can go again. It's going to swing in and form a new carbon-carbon double bond between these two carbon atoms. And then these electrons are going to go up onto the oxygen, just like that. And that will give us the following. Just like that. And you can see here, our electrons are now up on the oxygen, so let's count them. 1, 2, 3, 4, 5, 6, 7. Oxygen should have 6. This one has 7. 6 minus 7 would be negative 1. Our negative charge is there. And at this point in time, we are done. There is no further sequential resonance structures. Let's do the next one here. Now we've got a cation, so that means the electrons flow to the cation, okay, to the hole. We look next door. Is this atom part of a multiple bond? It is. Or does it have a lone pair? It's part of a multiple bond. Our electrons are going to flow towards the cation, just like that. That's going to give us the following. Putting in our hydrogens. Our double bond is now there. H, double bond, H. We got to go find our positive charge. It was here. Now we look 1, 2, 3, 4. Carbon should have 4. This one does have 4. 4 minus 4 is 0. This carbon, 1, 2, 3, 4 electrons around it. Carbon should have 4. Minus 4 is 0. How about this one? Again, look for the carbon that doesn't have enough things attached to it. We got 1, 2, 3. Carbon should have 4. It has 3 in this case. Therefore, it is deficient 1. This would be positive charge there. Are we done yet? Well, we got to look next door. This carbon is part of a multiple bond, so we do have another resonance structure that we can draw. Electrons are going to go from this double bond into the space between the two carbons to form a new carbon-carbon double bond. That's going to give us this, H, carbon. So we started here. I'm sorry, the carbocation started here. So we look 1, 2, 3, 4. Carbon should have 4. This one has 4. Therefore, it's no charge. This one, 1, 2, 3, 4. We're good here. 4 minus 4 is 0. How about this carbon? Well, again, 1, 2, 3. So we're 4 minus 3, which would be positive 1. So our positive charge is here. Are we done yet? Well, we look next door. This carbon isn't part of a multiple bond or have a lone pair, so we can't go that way. This oxygen does have a lone pair, so it could use those to donate, and that's exactly what it does. They swing in to form a new carbon-oxygen double bond. That gives us the following, H. So now we see where the cation went because we can't just make charges disappear. So our carbon here, 1, 2, 3, 4, it's good. Should have 4. It does have 4, so 4 minus 4 is 0. Our oxygen here, well, it should have 6. So how many does it have that it owns? Not total, but how many does it own? 1, 2, 3, 4, 5. So should have 6, has 5. 6 minus 5 is positive 1, and that is where our positive charge is. Can we go any further? Well, the answer is no, because this carbon is not part of a multiple bond, and it does not have a lone pair. Last one. Again, now we have an anion. Anions do the pushing. Okay, so we look next door. Does this atom, or is this atom part of a multiple bond or have a lone pair? I mean, we're in an anion, so it's more of, is it part of a multiple bond? The answer is yes, it is. So therefore, we can have additional resonance structures. Our anion is going to do the pushing. Electrons swing down to form our new carbon-carbon bond. These have to go out of the way. They're going to go onto the neighboring carbon atom just like that. And we draw our resonance structure, CH3, C, nitrogen, H, one pair there. Carbon, H. Like that. And you can see where we started was here. So if we look, 1, 2, 3, 4, carbon should have 4 valence electrons. This one does. It's going to be neutral. Same here, 1, 2, 3, 4. Should have 4, has 4, neutral. This carbon, you can see that's where the lone pair is, but if you didn't realize that, count them up. 1, 2, 3, 4, 5. Carbon should have 4. This one has 5. 4 minus 5 is -1. That's where our charge is. We got to look next door to see if we're done yet. Is this atom here part of a multiple bond? Or, in this case, is it part of a multiple bond? The answer is yes. So we can have an additional resonance structure. Electrons swing down to form our new carbon-carbon double bond. These electrons have to get kicked out of the way. They're going to get bumped up onto the nitrogen, just like that. And at this point in time, I'm going to move over a little bit, and that will yield the following structure. Shown there. And we got to find out where our anion is. It started here. This carbon's got 1, 2, 3, 4 electrons around it. Carbon should have 4. This one does have 4 valence electrons, therefore it's neutral. This carbon has 1, 2, 3, 4. 4 minus 4 is 0. This nitrogen should have 5 valence electrons, and it's got 1, 2, 3, 4, 5, 6. So it'd be 5 minus 6 is -1. Our negative charge is on the nitrogen. And we can go no further because we would be going to a hydrogen. You can't draw resonance structures to a hydrogen. So at this point in time, we are done.